Welcome everyone. In this presentation, we're diving into discriminant analysis. And no, it's not about being judgmental, though it does judge which category your data belongs to. Think of it as the sorting hat from Harry Potter, but for data scientists. It's been around since the 1930s, which in tech years makes it basically ancient, but don't let that fool you. This method still packs a serious punch. So, what exactly is this thing? Imagine you're at a party and there's this really perceptive bouncer who can tell just by looking at you whether you're VIP or regular admission. That's basically discriminant analysis. It looks at your characteristics and figures out which club you belong to. Unlike that awkward moment when you try to sneak into the VIP section, this method uses actual math. Specifically, it measures how far you are from each group's average. It's like social cliques in high school, but with statistics instead of drama. This method gets around more than your friend who works in consulting. Seriously, it's everywhere. Banks use it to decide if you're creditworthy. Spoiler, they probably already know about that pizza delivery bill. Doctors use it for diagnoses, which is way more serious than sorting gym members. Forensic scientists use it to classify ancient skulls, which honestly sounds like the coolest job ever. There's even been cases of disputed authorship where discriminant analysis played detective. The method has been classifying everything from bonds to customer types for decades. If there's a group to sort into, discriminant analysis is on the job. Here's our first example, and it's delightfully simple. A gym wants to figure out who's likely to splurge on that premium membership. You know, the one that comes with towel service, and maybe a personal trainer who judges you slightly less. We've got 24 members, half premium and half basic, and we're looking at how much they spend monthly and how many hours they work out. The magic happens when we draw a line through this data. Think of it like drawing a boundary between definitely upgrading and happy with basic, thanks. The discriminant analysis nailed it with only 3 mistakes out of 24. That's an 87.5% accuracy rate, which is better than my success rate at actually going to the gym. This is where the magic happens. The whole idea boils down to one simple question. Which group are you closer to? Imagine you're at a party standing between 2 groups of friends. You naturally gravitate toward the one you're closest to, right? Same concept here. We measure how far your data point is from each class average. We call that the centroid to sound fancy, and boom, you belong to whichever one you're nearest to. It's like those find your nearest store features, except we're finding your nearest statistical tribe. The key insight? Distance matters. And no, we're not talking about that I need space conversation you had with your ex. This is math distance. Okay, here's where we get a bit nerdy, but stick with me. Regular Euclidean distance, you know, the as the crow flies distance, has some serious flaws. First, it cares about units. Measure income in dollars instead of thousands? Completely different answer. It's like saying someone is 72 inches tall versus 6 feet. Same height, but the number looks way different. Second problem, it totally ignores how spread out your data is. And third, it pretends your variables don't talk to each other, which is like assuming your coffee consumption and your productivity are unrelated. Spoiler, they're not. Enter statistical distance, or Mahalanobis distance, for those who like to impress at parties. This bad boy fixes all 3 problems. It standardizes everything, accounts for spread, and handles correlations. It's basically Euclidean distance that went to grad school. Meet R.A. Fisher, the rockstar statistician from 1936. While everyone else was worried about the Great Depression, Fisher was out here revolutionizing classification. His big idea? Find a way to make groups as internally consistent as possible while making them as different from each other as possible. It's like organizing your closet so that all your t-shirts are together and they're clearly separate from your pants. The mathematical beauty here is that we're maximizing between group differences while minimizing within group differences. It's efficient, elegant, and has stood the test of time, kind of like a good leather jacket or the concept of pizza. The method creates classification scores for each group, and then it's simple. Highest score wins. Your data point goes to whoever claims it the loudest, mathematically speaking. Alright, let's break down the actual process because I know you're thinking, this sounds complicated. First, we calculate the average centroid for each class. Think of it as finding the center of each friend group at that party. Second, we compute the covariance matrix, which is just a fancy way of understanding how your variables relate to each other. Do people who spend more also work out more? That kind of thing. Third, we use all this info to create classification functions. These are your mathematical bouncers. Fourth, for every record, we calculate a score for each class. And finally, we do the obvious. Assign each record to whatever class gave it the highest score. It's like speed dating, but instead of finding love, you're finding the right statistical category. Much less emotionally complicated. Now here's where things get really useful. Instead of just saying you're in class A, we can say you're 78% likely to be in class A and 22% likely to be in class B. It's like going from it might rain to there's a 70% chance of rain, way more informative. We convert those classification scores into actual probabilities using a fancy exponential formula. Don't worry, software does this for you. The magic of having probabilities is that you can rank things. Maybe you want to target the top 100 most likely premium members for a marketing campaign, or generate lift curves to see how well your model performs, or adjust your cutoff threshold. Maybe you only want to classify someone as premium if you're 80% confident instead of just 50%. It's like having a confidence meter instead of just a yes-no switch. Much more flexible, much more powerful. Okay, confession time. Discriminant analysis has assumptions, and in theory, they matter. First assumption, your data should be multivariate normal. That means if you plot it, it should look like those nice bell curves you remember from statistics class. Second assumption, the correlation structure should be the same across classes. In other words, the way your variables relate to each other shouldn't be wildly different between groups. Now here's the good news that'll make you sleep better at night. This method is surprisingly chill about violations. It's like that friend who says they're vegan but will totally eat pizza at 2 a.m. As long as your smallest class has at least 20 records, you're usually fine. Binary predictors? No problem. Non-normal data? It'll probably work. The one thing that'll really mess you up, outliers. Those weird data points that are way off from everyone else. They're like that one person at karaoke who insists on singing opera, technically impressive but throws off the whole vibe. Time to grade our model. Just like your report card in school, but hopefully better, we need to evaluate how well this thing actually works. The confusion matrix is your best friend here. It's a table that shows you exactly where your model messed up. Did it misclassify premium members as basic or vice versa? You'll see it all. Then there's accuracy, just a simple percentage of how often you got it right. Easy to understand, though sometimes misleading if your classes are imbalanced. Lift charts are super useful when you're ranking things. They show you how much better your model is than just guessing randomly. Here's the critical part though. Always test on a validation set. If you evaluate your model on the same data you trained it on, you're basically grading your own homework. Of course, you'll think you did great. It's like practicing a presentation in front of your dog. Very encouraging, but not actually representative of how it'll go in real life. Here's where discriminant analysis shows off its flexibility. First up, prior probabilities. Your sample might be 50-50 premium versus basic members, but in the real world, maybe only 15% are premium. You can adjust for this. It's like recalibrating your expectations based on reality. Just add a little logarithm adjustment to your classification function and boom, your model now reflects the real-world distribution. Second cool feature, misclassification costs. Not all mistakes are created equal. If you're a bank, missing a credit defaulter costs you way more than rejecting someone who would have paid you back. Maybe it's 10 times worse. Discriminant analysis lets you account for this. You can literally tell the model, hey, this type of mistake is expensive. Please try harder not to make it. It's like having weighted grades in school where the final exam counts for 40%, some things just matter more. The best part? Both of these adjustments are super easy to integrate. Just a simple modification to your classification function, constants. Easy peasy. Plot twist. Discriminant analysis isn't limited to just two categories. It scales beautifully to multiple classes. Let's say you're analyzing customer churn risk and you want to classify people as low, medium, or high risk. No problem. Instead of one classification function for each of two classes, you get one for each of three classes. The logic stays exactly the same. Calculate a score for each category, and whichever score is highest wins. It's like those multiple choice tests where you have options A, B, C, and D. Except here, the algorithm is way better at choosing than you were on that test you definitely studied for. The confusion matrix gets a bit bigger. Now it's 3 times 3 instead of 2 times 2. But fundamentally, everything works the same way. You can have as many classes as you want, 4, 5, 10. Though let's be honest, if you have 10 classes, maybe you should rethink your categorization strategy. At some point, it's not classification anymore. It's just chaos with extra steps. Let's talk about why you should care about this old school method. First off, it's fast. We're talking lightning speed computation compared to modern deep learning methods that need to warm up your computer like it's mining cryptocurrency. Second, and this is huge, it's a small sample wizard. While other methods are crying because you only have 50 data points, discriminant analysis is out here saying, "That's all I need, baby." Research shows it's actually 30% more efficient than logistic regression when assumptions are met. That means you need 30% fewer records to get the same quality results. That's like buying stuff on sale, but for data. It also tells you which features actually matter, which is super useful for understanding your data and explaining results to your boss. The sweet spot for this method is small to medium datasets where your classes are reasonably well separated. If your data looks like 2 distinct clouds with some overlap, discriminant analysis is your friend. It's the reliable Toyota Camry of classification methods. Not the flashiest, but dependable, efficient, and gets the job done. And that's a wrap. Here is a recap. Discriminant analysis is all about measuring statistical distance to classify records into groups. It uses Fisher's brilliant linear classification functions from 1936, proving that good ideas never go out of style. It handles multiple classes like a boss, just creating more classification functions as needed. It's especially powerful with small datasets where other methods would struggle. Think of it as the efficient, compact car that still delivers when everyone else needs a full tank. And despite having some theoretical assumptions, it's surprisingly robust when those assumptions are violated. The method has been successfully used across countless fields for almost 90 years. So the next time someone tells you we need the latest, greatest neural network for a classification problem, remember, sometimes the old ways are still the best ways. Thanks for your attention.